Another day, another story. For hundreds of years, we've been able to predict the effects of gravity. But we had no idea how it worked until Einstein stepped in, painting a strange and unintuitive picture. In Einstein's view, gravity is far from a static, unchanging force. It is a fundamental part of the structure of the universe, which curves and twists and ripples as objects move and rotate and jostle about. The predictions of Einstein's theories have been validated time and time again. And now, 100 years after the formulation of his theory of gravity, another one of its predictions, gravitational waves, has been directly measured, despite Einstein's belief that we'd never be able to do this. In this topic, we'll explore Einstein's dynamic vision of gravity, including the recently measured phenomenon of gravitational waves. If you're unfamiliar with relativity, some of these concepts may boggle your mind. If so, we encourage you to keep pushing onwards, as it's one of the greatest journeys in the history of science. Let's begin by looking at why Newton's laws didn't provide a complete picture of gravity. Isaac Newton, 1642-1726, and Albert Einstein, 1879-1955, were pivotal in advancing our understanding of gravity. Newton published one of the most celebrated works of science, the Principia, in 1687. In it, he described that the force that pulls objects towards the ground is the very same force that underlies the motion of the planets and stars. To come to this conclusion, Newton imagined taking an object far from the surface of Earth, and throwing it. If you throw it with too little momentum, it will fall towards Earth, captured by gravity like we are ourselves. If you throw it with too much momentum, it will speed away from the planet, beginning its journey into the reaches of space. But with exactly the right momentum, you can throw it so that it falls continuously around Earth, around and around in an eternal tug of war. The object tries to continue in the path you threw it, but gravity keeps on pulling it back in. With the right balance, the object is now in orbit around Earth, just like the Moon, or like Earth around the Sun. Newton formulated this insight into a mathematical equation, known today as the law of universal gravitation. When combined with knowledge of geometry and Newton's other equations of motion, we can use it to make predictions about the movement of the planets, or the paths of comets, or how much force is needed to get a rocket to the Moon. We acknowledge Newton not just because of his idea, but because he formulated that idea into an equation that made predictions with greater accuracy than ever before. But it wasn't perfect. Newton's equations produced some incorrect predictions, and, more importantly, he didn't describe how gravity works the way it does. Newton was well aware of this when he said, "Gravity must be caused by an agent acting constantly according to certain laws. But whether this agent be material or immaterial, I have left to the consideration of my readers." More than 200 years after the Principia was published, the world was still without an understanding of gravity's mechanism. Enter Albert Einstein, a man who was to change the world in so many ways. But before we get to his work, we'll have to take one more detour. You can't tell if you're moving at a constant rate. In 1632, even before Newton published his now famous work, Galileo Galilei wrote about the relative motion of objects familiar in his time, ships. If you are in a closed room on a ship sailing at a constant speed and the ride is perfectly smooth, objects behave as they would on land. There's no physical experiment you could conduct to tell whether you're moving or stationary, assuming you're not peeking out of a porthole. This is the core idea behind relativity, and is the same reason why we don't feel our planet's movement around the Sun, or our solar system's movement through the galaxy. Almost 300 years after Galileo, Einstein pondered the consequences of relativity in the context of an important factor: the speed of light. He wasn't the only person who was pondering these topics. Other physicists at the time were aware that there were unanswered questions on this front. But it was Einstein who formulated a theory, his theory of special relativity, to explain existing phenomena and create new predictions. At first, special relativity may not seem to have much to do with gravity, but it was an essential stepping stone for Einstein for understanding gravity. Experiments during Einstein's time had shown that the speed of light appeared to be constant. No matter how fast you try and catch up, light always appears to zip away from you at almost 300 million meters per second. Why is this important? Well, let's imagine constructing a clock out of light itself. Two mirrors are placed opposite each other, and a tick of the clock is the time it takes for a particle of light to travel from one side to the other and back. Now let's imagine that your friend, who's on a spaceship zipping past Earth, has one of these clocks. For your friend, the clock seems to be working normally, the particles of light travel up and down, as expected, and time proceeds in its usual fashion. But from your perspective, watching the ship pass by, the light is moving both up and down and to the side, with the ship. The light travels a longer distance with each tick. So if, for the space traveler, light travels at 300 million meters per second but only has to travel up and down, and to the Earth-bound observer, light travels at 300 million meters per second, but must travel a longer, diagonal distance, then for the Earth-bound observer, the clock takes longer to tick. This effect is called time dilation. The faster you travel through space, the slower you travel through time. But whose time is really slowed down? Is it the person on Earth, watching his friend zip past in her spaceship? Or the astronaut, who argues she's staying still while the Earth flies by? Strangely enough, both viewpoints are valid, but only while both are in constant motion. To illustrate, let's assume that when the astronaut left Earth, she and her friend were the same age. When she leaves, the spaceship accelerates away from Earth. When she returns, the spaceship decelerates to avoid a crash landing. In both leaving and returning, the spaceship changes its frame of reference, and our astronaut can feel the change of motion. Experiments conducted inside the spaceship during acceleration and deceleration would show that something. Thanks for watching.